Okay, so we are going to continue to work through lecture set 4 today. We started lecture set number 4 on Wednesday, just near the end of class. And I just used the remaining time to kind of highlight what will be the key part of this lecture, which is this idea of ratio estimation. And we will see ratio estimation in two contexts. We will see it within the simple random sampling context and within the stratified random sampling context. So this estimation technique is a technique that we can utilize in both of the major sampling schemes that we have talked about so far. And then again, just for reference, I think I forgot to do this on Wednesday. This is the 26th. Okay, one other reminder before we get started here. So we have quiz number 2 on March 1, which is Monday. So for quiz 2, we will have the same options for writing that we had for quiz 1. So you can write in person, which would be in CCC 9-103. Or you can write online if you're not comfortable with coming to campus. As with the previous quiz, please let me know if you would like to write online. I assume the students that wrote online on the first one would like to write online again, but I would like you to confirm that with me. So I will just assume that you are writing in person unless I have heard from you. So far, I think I've heard from 3 or 4 students. So please let me know as soon as you can whether or not you will be coming to campus or writing from home. All right. So ratio estimation, what is it? Why are we studying it? The main reason that we are studying ratio estimation is because it allows us to conduct inference about a population parameter when we are missing key information. And it also allows us to include information from what we would call an auxiliary variable into our estimation strategy. This auxiliary variable is typically a variable that is strongly correlated with the variable of interest, which just means that it would add information rather than take information away from the estimation procedure. So we're going to see some examples of ratio estimation. Again, we have 2 general scenarios using ratio estimation when we are lacking some key statistic or population parameter, and ratio estimation where we're interested in actually talking about the ratio between these 2 variables in our data set. So in that context, which we can think of as situation number 2, we're actually going to estimate the population ratio directly. At the end of last class, we briefly talked about the first situation where we are interested in using ratio estimation to estimate a population parameter, for example, the total, but we are missing a key piece of information, for example, the population size. So we know that from SRS, okay, so from SRS, we know that our estimate for tau, we'll just call it tau for now, is equal to n times mu hat. Now, if we are missing capital N, of course, estimating tau is going to be very difficult. Ratio estimation provides us with a way to estimate tau without having capital N. And again, this would be the first situation or the first scenario in which we would be interested in using this approach. So we can show through some fairly simple derivations why this is true. So for example, on the slide, we have tau y divided by tau x. Okay, so this is tau, the total for the variable of interest. So we're letting y be the variable of interest. Okay, and then we're going to let x be the auxiliary variable. or the correlated variable. I definitely spelled auxiliary wrong. Right? So we know that tau is equal to capital N times mu. This is going to be true for both the auxiliary variable and the variable of interest. So when we take the ratio of tau y to tau x, we then have capital N times mu y divided by capital N times mu x. Capital N is going to be the same quantity in this case because you can effectively think of this of the variable of interest and the auxiliary variable as being well, two variables from the same population. So if we collected a simple random sample, say of size 50, we would have 50 observations for y and 50 observations for x. So it follows that they have the same population size. So you can see that we have cancellation here. So we now have tau y over tau x is equal to mu y over mu x. And if we rearrange, we then have tau y is equal to mu y over mu x times mu x. So if we replace mu y over mu x with their estimates, then we then build an estimate for tau y. So this ratio of mu y to mu x, this is in our ratio estimator, or the ratio that will be of interest to us when we are studying a mean or a total, because we can see that even when studying the total, we get cancellation of the population size. Okay, so that would be the first situation in where we would want to use ratio estimation to estimate some population quantity, for example, the total, when we are missing a key piece of information. The second situation is simply where we want to actually make an estimate of the ratio itself. So there might be situations where we are interested in talking about the ratio of the population parameter or of the variable of interest to the auxiliary variable. So in this case, we can define the population ratio as theta. So theta is now our parameter of interest. Okay. So if we have a population of size capital N, we collect a simple random sample of size little n. If in that sample we are able to collect a measurement of y and x, we can then estimate the population ratio by taking the ratio of the mean of the variable of interest over the mean of the auxiliary variable. So we define our estimate of the ratio of theta to be mu hat y divided by mu hat x, and the estimator for theta, of course, would be theta tilde, which is equal to mu tilde y over mu tilde x. All right, so to utilize this estimate, we have to, of course, know its properties. So just like before, the first thing that we're going to do is define the properties of the estimator that is of interest to us. So we are going to look at the properties of theta tilde. Now, as you will probably imagine, we will be able to show that the estimates here, that the estimator is unbiased, and we will be able to define a variance estimator for theta tilde that we can utilize to bound the estimates coming from an experiment where we are interested in estimating the population ratio. Okay, so in this particular situation, we won't be able to use direct application of the expected value operator or the variance operator. Instead, what we're going to do is use a Taylor expansion about the values of interest. And then through that Taylor expansion, we can derive results for the expected value of the estimator and for the variance of the estimator of interest. All right. Okay, so just like before, the goal here is find the expected value of theta tilde and the variance of theta tilde. All right. Okay, so some of you may have seen the Taylor expansion before, so I'm going to just highlight the properties of this. So from a Taylor expansion of f of x, y about x0, y0, we have f of x, y is approximately equal to f of x0, y0 plus del f x0, y0 by del x minus x0 plus del f x0, y0 divided by del y minus y0. Okay, so if f of xy is equal to y over x, then del f of x comma y divided by del x is equal to y over x. Or no, sorry, it's equal to negative y over x squared. And df x y divided by dy is equal to 1 over x. I wonder if I could just squeeze this part up real quick here. All right. Okay, so now what we'll do is we'll utilize these expressions and the actual quantities that are of interest to us in the ratio estimation procedure to find an expression for the expected value. And then we'll do a similar thing for the variance. So for example, if we let x, y equal mu tilde x, mu tilde y, and x0, y0 equal mu x, comma mu y, then theta tilde is approximately equal to mu y over mu x plus 1 over mu x tilde minus mu x sorry, 1 second. Dx. This is dy. try and keep it in order here. This is our dy. And then we need the negative term. So this would be minus mu y over mu x squared, mu tilde x minus mu x. Make sure. Okay. Okay, so now what we've basically done is we've taken this general Taylor form about the point x0, y0. We've let x0, y0 be the estimators that are of interest to us. Well, we've let them be the parameters that are of interest to us, and we let x and y be the estimators. Now what we've derived is an expression for theta tilde. So what we're going to do with this expression is we're going to take the expected value of this term to find the properties of the estimator. Okay, so now let's compute the expected value of theta tilde. So we have the expected value of theta tilde is approximately equal to mu y over mu x minus mu y over mu x squared multiplied by the expected value of mu tilde x minus mu x plus 1 over mu x times the expected value mu tilde y minus mu y. Okay, now we'll have mu y divided by mu x minus mu y divided by mu x squared multiplied by the expected value of mu tilde x minus mu x plus 1 over mu x, the expected value of mu tilde y minus mu y. Okay, and then we can see that these terms here are both going to go to 0 because the expected value of mu tilde y is mu y. We're using simple random samples, and we've already derived the expected value of the estimator of the mean in the SRS case. We know that it's unbiased. So both of these terms will go to 0. And then through those simple cancellations, we can show that the expected value of the ratio estimator is approximately equal to mu y over mu x. So then we can say, therefore, therefore theta tilde is approximately unbiased. All right. Does anyone have any questions so far? We cannot show if it's exactly unbiased because we cannot find the expected value of mu tilde y over mu tilde x directly because they are both random variables. So we can only show in this case that it's approximately unbiased, at least as far as I know. Any other questions? All right, so let's set this up the same way I did before. Let's compute. Okay, so we'll write, let's compute the variance of theta tilde. So we're going to have the variance of theta tilde is approximately equal to. Okay, so now what's going to happen is we're going to have the variance of that long expression that we had from the previous slide. So we'll have this term minus mu y over mu x squared, mu tilde x minus mu x plus 1 over mu x, mu tilde y minus mu y, right? Okay, so variance is closed under addition and subtraction. So in the context of the problem that we're looking at, this term is going to be gone. So the variance of the first part here, sorry, there's a better, that explanation isn't going to quite work. Okay, sorry, I need to explain this slightly differently. Okay, so first, variance is closed under addition and subtraction, right? We want the variance of the terms that are actually estimators. So the variance operator is going to apply to the mu tilde x, and it's going to apply to the mu tilde y, because those are the only two variables that are random. So when we compute the variance of the term as we have it written on the slide, the mu y over the mu x, the leading term, this is a constant because these are two parameters. So this term is actually just going to fall off of the expression. Then what we need to do is we need to simplify the inner term to only include the parts that actually have the mu tilde x and the mu tilde y. So you can see that there's going to be a term mu y over mu x squared times mu tilde x, and there's going to be a term 1 over mu x times mu tilde y. But the other terms are all going to be constant with respect to the estimators. So this thing here can simplify to the following expression. 1 over mu x, and then we will have mu tilde y minus mu tilde y over, mu y over mu x times mu tilde x. Okay. So that gives us the mu tilde x term, and that gives us the mu tilde y term. Yeah. And you can just see that all I've done here is I've just pulled the 1 over mu x out because that's constant with both terms. And I've rearranged because of the negative sign. Okay, but again, the idea here is that variance is closed under addition and subtraction. So the variance operator is only going to apply to the terms that are actually random. The terms that are random are the mu tilde x and the mu tilde y. So effectively, if you expand what's inside the variance operator on the first line, you will see that mu tilde x multiplies by mu y over mu x squared, and mu tilde y multiplies by mu x. So those are the only two terms that we actually need in the second line. And then I've just made a simplification to collect like terms essentially on that second line. All right, so now we can show that this thing is going to be approximately equal to 1 over mu x squared. So the variance operator also squares constants, hence the 1 over mu x squared. And then we're going to have the variance of mu tilde y minus theta times mu tilde x. Okay, so now what we're going to do is introduce a term that will essentially collect the information that's required to compute this variance operator. So we're going to write let little ri equal yi minus theta xi. Okay. So then mu of r is equal to 1 over capital N times the sum of I in u of the ri. So mu of r can also be written as mu y minus theta times mu x. Therefore, mu tilde r is equal to mu tilde y minus theta times mu tilde x. And then we can say from SRS, the expected value of mu tilde r is equal to mu r, and the variance of mu tilde r is equal to 1 over n minus little n times this variance of the estimator divided by little n. Okay. So we drove an approximation for the variance. That was the first part. So we have this term 1 over mu x squared times the variance of mu y tilde minus theta mu x tilde. Okay, so how do we handle this mu tilde, how do we work with this mu tilde y minus theta times mu tilde x? We introduce a term that we're calling ri, which represents the difference between yi and the ratio times xi. So it follows that the mean of these ri terms is essentially just the mean like any other term. So it's the sum of all of the ri's divided by n in the population. So from that, we can show that mu r can also be written as mu y minus theta times mu x. And this is a fairly easy thing to do because you're just taking the sum across all of the yi minus theta xi across the sampling frame and then dividing by capital N. So it makes sense that mu r would have this separate expression. Okay, so the estimator for mu r would be written in the traditional way. So basically just we would estimate the mu tilde y and the mu tilde x. And then from simple random sampling, we can show the expected value of these terms. have the same functional form that we saw in the SRS case. All right, so now we just need to put these ideas together. This theta r squared term here is going to be written as, so this is going to be where theta r squared is equal to 1 over capital N minus 1 times the sum of I in U of the Ri minus the mu r squared. And this can therefore also be written as, so this is equal to this, which is also equal to the following. Okay, so we're going to have yi minus theta xi minus mu y minus theta mu x squared. So the estimate for sigma r squared can be written as sigma r hat squared is equal to 1 over little n minus 1 times the sum of I and s okay, yi minus theta hat xi minus mu y hat minus theta hat minus or times mu hat x. Okay. And then we say let theta hat equal mu hat y divided by mu hat x. Then sigma of the standard deviation of the ratio squared, or the estimate of the standard deviation of the ratio squared is 1 over n, the sum I and s of yi minus theta hat xi squared. Which is a nice simplification from the original expression. So we get lots of cancellation from the introduction of the theta hat. All right, and now we can finish this off by saying, therefore, the variance of theta tilde is approximately 1 over mu squared x, mu x squared, multiplied by the variance of mu y minus theta mu tilde x, which is approximately 1 over mu x squared, the variance of theta, of mu r tilde. Which is approximately 1 over mu x squared times 1 over little n capital N sigma tilde r squared divided by little n. This comes from this, yeah. And then this thing is that, and then that thing we wrote, yeah, okay. And there we have it. So as usual, I mean, this is typically the case when we work with these estimators, but we showed that the estimator of interest is unbiased. So the original, well, approximately unbiased. So we started off by showing through a Taylor expansion about the point of interest that we have an approximately unbiased estimator for the population ratio. And then the next thing that we did is we drove the variance. And of course, we need the variance so that we can bound our estimates. Now, in this case, what we did is we started off using the same expansion, and we showed that the variance of the estimator can be written as 1 over mu x squared times the variance of mu tilde y minus theta times mu tilde x. That's what we have written a little bit above. I just don't want to move this slide right now in case anyone is copying this. And then what we did is we said, okay, well, let's introduce this variable Ri, which represents the differences between y minus the estimate or the ratio estimator times x. From that, we drove mu r. From that, we were able to show that the properties of mu r will be effectively the same as what we saw for our simple random samples, our simple random sampling estimators of the general variable of interest. Once we had established the variance of mu r, it was easy to show that the variance of the ratio estimator is effectively going to have the exact same form, except we have this 1 over mu x squared term out front. So the approximation that we're going to be using throughout the study, it looks very similar to what we had in the simple random sampling case, except that we have the 1 over mu x squared term out front. And the sigma, the estimate of the ratios is going to be 1 over n minus 1 times the sum across all values in the sample of each yi, which is the variable of interest, minus the estimate of the ratio times the auxiliary variable squared. So we have a slightly different standard deviation measure that we would have to compute if we were doing this from scratch. All right. So some good mathematics for a Friday morning. Does anyone have any questions? Oh, man. Okay, I'm not seeing any. So we can finish today off with a practical example. So just seeing an application of these formula. So to summarize, we have that the expected value of our estimator of the population ratio is unbiased, so it's equal to mu y over mu x, well, approximately equal to. We have the variance of the estimator of the ratio as 1 over mu x squared times the finite population correction, which will obey the standard rules of a finite population correction, multiplied by the standard deviation of those ratio values, so the RIs, multiplied by the variance of those ratio values, the RIs over little n. We can write our point estimate for theta just as the ratio of our estimates for the variable of interest divided by the auxiliary variable. The standard error of our estimate will be found in the usual way, so we'll just take the square root of our estimate of the variance, which would just be found by plugging in our estimates for mu x and our estimate of sigma r squared. And then we can bound our ratio estimate in the usual way. So we can multiply by some Z alpha over 2 value times that standard error. In most often, of course, this will be a 95% interval. Okay, so as an example of this, we have the following illustration. The grain farmers of Ontario want to estimate the corn yield of 1,000 farms. A sample of 50 farms is taken via SRS. The amount harvested and the area of the farm are measured for each farm in the sample. Okay, so harvest value here will be the Y, and the area here will be the X. Okay, when we use ratio estimation, we need there to be an evidence of a linear relationship. So earlier in the lecture, I noted briefly that this approximation or this technique works best when there's a strong correlation between the variable of interest and the auxiliary variable. When we say strong correlation, we mean linear correlation. So in this case, what can be helpful is creating a scatter plot of the information. The other thing that we could do is calculate the correlation coefficient between the two values. If we calculate the correlation coefficient between the two values, we can then do things like build confidence intervals around the correlation coefficient to determine if there's significant evidence of a correlation between the two. So in this case, we're just using the most the most naive approximation. We're looking at the graph. If we put a straight line through the middle of this, we can see here that the data appears to be positively linearly correlated. Now, the other thing that we want to check when we're using ratio estimation, and this is a point that we will see a little bit later in the slide when we talk about regression estimation and the difference between the two. But with ratio estimation, we also want the relationship to cross through the origin. Okay, so now the reason for this will become clear later when we talk about regression estimation. But if we have a strong positive association and the relationship does not cross through the origin, then we would actually want to adjust for that y-intercept term. Okay, but again, we'll see how we're going to make that adjustment later. Very similar idea to the ratio estimation idea, except that we include information about the intercept on, well, the intercept that would arrive from studying the linear relationship between the two terms. All right. Okay, so we want to calculate or estimate the population ratio between the harvest and the area. Okay, so this will be done just by applying the properties that we have just found. Okay, so for example, to estimate theta, we have theta hat is equal to mu hat y over mu hat x. This is going to be mu hat harvest divided by mu hat area. This will be 28,307.76 divided by 183.08. And that should give us a value of approximately 155 bushels per acre. I mean, made some, actually, I shouldn't be so cavalier with rounding, even though it sounds nice as a whole number, but it would be 154.62. Okay. All right, so the next thing we can do, as per usual, is we can bound our estimate. So this will be done in the normal way. So to bound estimates, we have capital B is equal to 1.96. So we'll use a 95% confidence interval multiplied by the standard error of theta hat. All right, so this will be 1.96 multiplied by the square root of 1 over mu x squared times sigma hat r squared over little n. Okay, so notice here that when we check the FPC, we have 1 minus little n over capital N is equal to 1 minus 50 over 5,000, I believe it was. Let's check that real quick. Oh, 50 over 1,000. Okay, which is equal to 0.95. So we can ignore the FPC. Since the rule for the FPC is we can ignore it when 1 minus little n over capital N is greater than or equal to 0.95. So we're right on the cutoff there. Okay, so this gives us 1.96 multiplied by the square root of 1 over 183.08. Multiplied by, that would be 7,623,296 divided by 50, which is equal to 2.132, 2.133. Therefore, a 95% CI for theta is going to be approximately 152.867 to 157.133. Cool. All right. So now we have, we've seen the derivations of the estimators. Well, we've seen the derivations of the expected value of the estimator and the variance of the estimator when we are interested in estimating the population ratio. And we've seen an illustration of how we would go about estimating the population ratio from a simple random sample. And hopefully you'll find that this illustration is very similar to the kind of illustrations we've seen before. I think that in general, the actual examples tend to be pretty repetitive in this course, but this topic is pretty interesting, I think, just because you have that underlying correlation that has to be assessed between the target variable and the auxiliary variable. So I like that aspect of it. And I think once we get to the regression, the regression estimation part of the unit, I think that's a very interesting application as well, because you can see how we can basically use regression estimation in a different context, but adjust for the intercept when we study the relationship between the two variables. All right, so I'll stop there for today. So on Monday, we'll have the quiz, and then next Wednesday, we'll pick up with the next example. So we'll see another example of ratio estimation before we move on to the next term. So that will serve as a bit of a refresher. Again, please let me know your preference for the quiz if you haven't done so already. If I don't hear from you, I assume that you will be there in person. And if you have any questions, please let me know. Otherwise, have a good weekend, and I will talk to you guys next Wednesday officially, but I will probably see most of you on Monday. Take care.